am Tulika Banerjee. Today I bring you the next learning episode on an important unit of the paper titled Fingerprints, that is, Preservation of Fingerprints, Arson. Let us now look at the modules which we will be covering today. So, our first module is regarding soot removal techniques. The second module is regarding effects of flammable liquids on latent friction ridge impressions. The third module is regarding recovery of latent friction ridge impressions, and the last module is of conclusion. We will cover these modules one by one. Often the first step in examining arson exhibits for friction ridge impressions involves soot removal. In the year 1938, Harper developed friction ridge impressions by simply brushing the soot off the surface, allowing the carbon particles to adhere to the oily residues in the ridges. He further explored the effect of elevated temperatures on friction ridge impressions placed on a variety of different substrates, including glass, porcelain, metal plates, enameled metal, and painted and unpainted wood. He observed that friction ridges quickly covered with a layer of soot were more likely to survive than the exposed impressions, as the soot appeared to prevent evaporation of the friction ridge matrix. In addition, Harper exposed soot covered friction ridges on metal surfaces to temperatures reaching approximately 500 degrees centigrade and discovered that on washing with water, the ridges appeared to be burnt into the surface and could not be removed even by rubbing. After the surfaces dried, soot removal was completed by gentle brushing. Although this study did not accurately record the experimental conditions or thoroughly examine the effects of elevated temperatures on recovery of aged friction ridges, but the study does refer to 3-month-old friction ridge samples that were exposed to fire. After being covered in soot, they were developed by washing, drying, and brushing. If the print was allowed to evaporate to dryness as a result of the fire prior to soot deposition, then the friction ridges could not be recovered. The first report describing retrieval of latent friction ridge impressions from an arson case did not appear in the literature for several decades. In 1978, McLeod described the processing of a soot-covered unbroken soda bottle that was purported to be a Molotov cocktail. Molotov cocktail is a form of explosive substance recovered from a partially burned apartment building. The debris and soot were removed by brushing the surface with a fiberglass fingerprint brush using soft, gentle strokes, which revealed soot developed friction ridges impression on the rippled glass bottleneck. Remaining soot was removed by washing with soap and water. Attempts to lift the impression from the surface resulted in unidentifiable images due to the rippled texture of the substrate. 1 year later, Vaughan promoted rinsing soot-covered exhibits such as glass, doorknobs, flammable liquid containers, and car door handles under running water, claiming that fingerprints appeared etched into the glass. The presence of gasoline and or the kerosene on the surface of the substrate was reported to decrease the effectiveness of this recovery method, most likely due to the hydrophobic nature of these fuels that would have repelled the water from the surface. Soot removal techniques were further developed by Thornton and Emmons, who suggested the use of lifting tape to remove the soot of remaining on the friction ridge impressions that were only partially revealed by water rinsing. The method was reported to work well for soot covered latents on metal and glass surfaces. In 1994, Smonfield tested the water rinsing technique using deliberately set incendiary fires involving everyday household items with latent fingerprints deposited onto the surfaces. Kerosene gasoline mix was used to start the fires, and typical fire suppression techniques were employed after intense heat and thick black soot was allowed to develop. Items closest to the fire revealed no ridge impressions on visual examination, whereas surfaces exposed only to heat and soot but no flame revealed many friction ridge impressions following water rinsing. Water rinsing revealed several fingerprint impressions which were further enhanced by the application of lifting tape. These impressions were burned onto the surface and could not be removed by aggressive rubbing. Again, it was observed that soot acted as a protective layer, providing it from of this latent friction impression before the surface experienced flames. In some circumstances, the formation of the soot layer helped to bake the friction ridge impression onto the metal surface. Wiley reported immersing the soot covered latent friction ridge impressions on glass into a 2% sulfosalicylic acid solution to fix the latent ridges. The glass was then immersed into a sonic bath containing 0.1 molar sodium hydroxide solution to remove the soot layer from the baked on fingerprints. The technique was tested using a mock living room fire scene in which the neutral plane of the fire was allowed to reach the floor level before the fire was extinguished. This allowed significant smoke to develop. A total of 18 sets of fingerprints were recovered from the glass bottles using this soot removal method, which were processed with either powder or with cyanoacrylate and brilliant yellow 40 or BY40. Based on successful yield experiences using sodium hydroxide wash solutions to remove soot layers without significantly damaging friction ridge impressions, Stowe and McGurry published an extensive study of soot removal techniques, including sodium hydroxide wash solutions, that is around 1% and 2%, ultrasonic water bath and vacuum suction, pure gasoline and a 1:1 mixture of gasoline and motor oil were used to contaminate the finger marks as well as being the flammable component within the glass incendiary devices. In the initial laboratory tests, contaminated and natural finger marks on glass substrates that had been subjected to controlled burns were examined using aluminum powder, SPR and Sudan black. Similar tests involving burning of a cotton or polyester sheet to produce soot were performed to compare the soot removal methods. Washing the soot with 1% and 2% sodium hydroxide solutions allowed recovery of both the contaminated as well as the natural finger marks. The 30 minutes water ultrasound bath failed to produce finger marks with the gasoline or motor mix, that is 1:1, but was successful for all other tests. In field test, friction ridge recovery was attempted after the glass incendiary devices were detonated, which resulted in much heavier contamination due to the accelerant. Under these conditions, the ultrasonic water bath, the vacuum and soft brush soot removal techniques did not perform as well as the 1% and 2% sodium hydroxide wash solutions. The researchers observed that when applying the sodium hydroxide solutions, care must be taken to avoid washing away the ridge details. Blee and co-workers compared numerous soot removal processes, including many that have already been described, that is, washing under running water, ultrasonic water bath, washing with sodium hydroxide solution followed by lifting tape, light brushing and pencil eraser. They also tested commercial soot removal methods such as clean film TM, cleaning sponge, epsorine and microsyl TM. A sequential soot removal process was recommended in which the least destructive methods must be tried initially, followed by those considered most likely to destroy both fingerprints and DNA. For all substrates, light brushing with a soft fingerprint brush to remove the loose debris was recommended so that subsequent soot removal techniques would be more effective. If the non-porous surface is flat and the exhibit has a simple shape, then application of flexible lifting tape using a roller is found to work best. The presence of flammable liquids on surface of the substrate has been reported to decrease the effectiveness of soot removal techniques. The recovery of soot developed friction ridges by water rinsing described by Vaughan was compromised by liquids such as gasoline and kerosene. The hydrophobic nature of these flammable liquids repels water from the surface, impeding the soot removal. In contrast, Tyransky and Petracco believed that the presence of gasoline in a plastic bowl used to transport and distribute gasoline throughout an apartment that was subsequently set on fire had created a plastic friction ridge impression in the rim of the plastic bowl. The plastic bowl was slightly soluble in the gasoline, and the action of carrying the gasoline filled vessel had resulted in a molded impression being left in the plastic. The plastic bowl was slightly soluble in the gasoline, and the action of carrying the gasoline filled vessel had resulted in a molded impression being left in the plastic. The impression was retrieved using silicone casting materials to create a three-dimensional impression, which was transferred to white paper by covering the surface with black ink. The friction ridge impression was identified to a suspect in the arson case. Isto and McGarry prepared Molotov cocktails using clean glass bottles that had both good and poor quality friction ridge impressions placed on the glass and plastic labeled surfaces. The bottles were carefully filled with gasoline or a gasoline motor oil in the ratio of 1:1 mix, and a cotton or polyester wick was inserted into the neck. Each Molotov cocktail was ignited, thrown against a pre-cleaned detonation area and allowed to burn out naturally. Over 90% of the contaminated glass fragments from each bottle were recovered and subjected to different soot removal techniques before friction ridge recovery with cyanoacrylate or BY40 was done. The researchers observed that it was particularly difficult to develop marks which had been exposed to the gasoline and motor oil mix due to the persistence of the oil on the surface. They observed the greatest success at recovery from these heavily contaminated friction ridge impressions when the glass fragments were soaked in 2% sodium hydroxide, sometimes for up to 30 minutes. Arson noted the accidental development of latent fingerprints on magazine paper resulting from the heat of a fire and illustrated finger impressions that were identified to the arsonist. Brown etc. al. observed that rapid heating of latent fingerprint impressions on a variety of porous surfaces in air over a temperature range of 220 to 300 degrees centigrade resulted in fingerprints that initially could be seen to fluoresce under green illumination at a wavelength of 505 nanometers, but with continual heating would eventually appear dark brown under white illumination until they lost contrast due to background charring. The researchers noted that these observations held for both eccrine and sebaceous rich impressions. In contrast, a study involving a variety of aged latent fingerprint impressions deposited onto white recycled paper exposed to longer heating regimes at lower temperatures, that is around 160 to 180 degrees centigrade, compared to studies of Brown etc. al. showed that only the eccrine component fluoresced. In the early 1980s, it was suggested that simply breathing onto the arson exhibit could rehydrolyze dried friction ridges and improve the adhesion of fingerprint powders. Shelef etc. al. examined the ability of several friction ridge detection techniques, including a small particle reagent, cyanoacrylate and BY40, silver black powder, crystal violet and forensic light source examination to detect freshly deposited impressions that had been briefly immersed in a variety of fire accelerants. Some of the friction ridges following exposure to the accelerant were left for several days before being processed. The researchers were able to recover 80 to 90% of the 5-day-old impressions and 50 to 60% of the 13-day-old impressions using either a small particle reagent or cyanoacrylate technique. Although the cyanoacrylate process showed a slightly improved performance compared to the SPR, the cyanoacrylate technique was abandoned as it was difficult to implement at the scene of crime. Simulated Molotov cocktail exhibits prepared by filling glass bottles with different fuel mixes were thrown against a test wall and either were allowed to burn out, were extinguished or were not ignited. The glass surface was examined using the following sequence of techniques such as visual examination under white light, forensic light source and cyanoacrylate, followed by vacuum metal deposition method or the VMD technique. It was reported that removal of the soot layer without impairing the friction ridge impressions was difficult. No data on the performance of specific detection techniques were provided, except that nenhydrin proved to be very effective at recovering latent friction ridge impressions on the paper labels. Aluminium powder, SPR and Sudan black were used to detect both natural friction ridge impressions and those contaminated with gasoline and gasoline or motor oil mix in the ratio 1:1 that had been subjected to controlled burns and sodium hydroxide wash solutions for soot removal. Both aluminum powder and SPR performed well, although adding motor oil to the incendiary mixture resulted in residue on the glass surface that prevented either development technique from being effective. In field tests, friction ridge recovery was attempted using cyanoacrylate and BY40 mixture after the glass incendiary devices were detonated, which resulted in much heavier contamination of accelerant. Under these conditions, friction ridge recovery was compromised but still possible. A recently published comprehensive study regarding the recovery of friction ridge impressions from arson was reported by Blee and co-workers. Rather than comparing existing methods of friction ridge recovery, the researchers first tried to establish the range of temperatures and exposure times for which latent friction ridges can survive. They developed a best practice for soot removal and subsequent friction ridge recovery on a variety of non-porous and porous substrates likely to be encountered at a typical arson scene. All arson examinations should begin with a thorough visual inspection, since the action of heat and soot can develop friction ridge impressions on exhibits. The development may be due to preferential soot deposition onto ridges, heat development of friction ridges on paper, and impressions being baked onto metal surfaces. Black or white powder suspensions proved to be the best treatment for non-porous surfaces exposed to temperatures up to 200 degrees centigrade. These methods were also effective for adhesive substrates. For non-porous substrates above 200 degrees Celsius, superglue fuming was the most effective technique, providing the surface was dry, and VMD was a technique of choice if the surface had been wet. For porous substrates, DFO was the best performing method, providing the surface had not been exposed to water. Physical developer was the reagent recommended for porous substrates that had been wet. Near infrared imaging using a near infrared sensitive camera and filter cut on wavelengths of 750 nanometers or above proved useful for charred paper. We know that latent friction ridges are typically comprised of chemicals secreted by the eccrine and sebaceous glands plus the miscellaneous contaminants. In addition, it is often misstated that physical evidence will be completely consumed during the progress of the fire, and subject matter experts often assume that charred or soot covered fire debris offers no hope for the detection of friction ridge impressions. So, several studies have been carried out to decipher the latent impressions from an arson scene. These studies also concentrate upon the process of removal of soot and application of certain reagents for the development of latent print impressions. Dear students, with this module of conclusion, our chapter comes to an end. I hope you all have enjoyed this chapter and gained valuable information regarding preservation of fingerprints in case of arson. I am sure you all have understood the central idea behind this module. The main objectives of the lecture was to familiarize the learners on how fingerprints are preserved in case of arson. In addition to it, you also got to know about the various soot removal techniques and how flammable liquids affect the finger ridge impressions. Also, you studied about how the finger ridge impressions can be recovered from arson cases. Do keep in mind what we discussed today. I will be back with one more lecture in the series. If you want to learn more and enhance your knowledge, you may log on to our website www.cec.nic.in for MCQ, quizzes, LORs, etc. Make sure you revise the modules frequently so that you master the topic well and take up the exercises. Thank you for your time today. I will see you in the next lecture. Keep learning, work hard and do revise the chapter. Goodbye.